All right, we're back 52 weeks of Swift, and I'm going to be talking about structures and classes. As always, I'm not 100% sure of the content. I'm going to learn it at the same time as you if you're paying attention. So I'm going to go ahead and share my screen here. Let's go ahead and start here and take a look at this. So to start off with Swift here, you can see structures and classes are general purpose and flexible constructs that you use as building blocks of code. And just a couple things I'll add here is that what is interesting about classes and object-oriented programming is for distributed computing, in my opinion, doesn't make a lot of sense to do object-oriented programming. Functional programming makes more sense, but with a language like Swift, which is heavily integrated into UI development, classes do make a lot of sense. And so in this case, it really does make a lot of sense to understand about object-oriented design because this is the appropriate use case for it. So in the note here, they say that an instance of a class is traditionally known as an object, but with Swift structures and classes, they're much closer in functionality in other languages. And much of the chapter here describes functionality that applies to instances of either a class or a structure type. So because of this, the general term instance is going to be used. So instead of object, they use instance for both classes and structure. So this is pretty cool. I'm probably going to learn some cool stuff today. To start with, we have structures and classes in Swift that have many things in common. Define properties to store values, define methods to provide functionality. Subscripts provide access to their values using this syntax, and defined initializers to set up their initial state, etc. But in general here, classes have additional capabilities that structures don't have. They can do inheritance, which enables one class to inherit the characteristics of another. So again, this is where object-oriented programming that can be really useful. Typecasting enables you to check and interpret the type of a class at runtime, and deinitializers enable an instance of a class to free up any resources it's got assigned. Reference counting allows more than one reference to a class instance. So the additional capabilities for classes support at a cost of increased complexity. As a general guideline, prefer structures because they're easier to use than classes. So I do agree that object-oriented programming can be massively complex, and that really is a problem. The definition, though, here is struct looks the same as a class. You just put the struct keyword in for a struct, and you put the class keyword in for a class. So here we go. Here's an example of a structure definition and a class definition. For structure, right here, we would say inside var, right, we have a mutable variable, width and height. And then you have in class here, you have something that looks very, very similar. So let's go ahead and look at a struct first. Let's go ahead and paste that into our code here and take a look at what that does. And I'm actually going to hide this menu over here. I'm going to make my browser. There we go. Perfect. And I'm going to grab both a struct and a class, copy this and paste it in. And there we go. We got both of them instantiated. And so in this example here, we have a new structure called resolution, and we can make an instance of it inside of the class. And this structure has stored properties called width and height. And these two properties are inferred to be type of an int because the initial value is 0. And this is a good example of creating a new class called video mode. And if we want to go ahead and make an instance of those, let's go ahead and do that. So we'll use let. So the difference here would be that in the case of the mutable variables, the var, because we're going to make instances of that, those would be vars. But in this case, we want to create immutable instances right here, and we're going to use the let keyword. And so structures and classes both use initializer syntax for new instances. And we can see here that I could play around with this if I wanted to, and I could say sum resolution, and I could do a dot. And then that's one of the nice things about objects or instances is that they have those properties associated with them. And now if I put height, right, we see that I could actually print this out if I wanted to, and it's going to be 0. But if I wanted to change it, I want to mutate it. And let's go ahead and do that. Let's change that attribute, and we'll say equal to 100, right? And now we print it out, and we should see in this particular example, it says cannot assign because let is a constant. Aha. So we've run into an issue here, which is because this was initially created with a let, it's going to have an issue. So let's go ahead and change it to a var, and let's see what happens. And in this particular scenario, it looks like we're now able to change it. So depending on whether you make an instance that's mutable or immutable, you're going to be able to change it or not change it, which is also kind of cool. Accessing properties here, in this case, you can access them by, which is essentially what we just did. You can access the attributes and print them out. The other thing you can do is you can drill down into sub-properties, such as the width property and the resolution of the video mode. And so in this case, if we wanted to do that, we could actually print that out. Let's go ahead and print that out. There we go. And the width of some resolution, the width of some video mode, perfect. You can also use the dot syntax to assign a new value to a value of a variable property. Some video mode resolution width is 1280. Let's go ahead and do that. Let's set this up, and we'll say new block here. So some video dot resolution dot width, we can go ahead and set that, and we see that we're able to set that variable that's been on top of the resolution attribute, which also has an attribute called width. You can do member-wise initializers for structures. So all structures have automatically generated member-wise initializers, which you can use to initialize member properties. So in this case, we'll do this. We'll go ahead and say let VGA. Go ahead and put this in there. There we go. And we can type in print VGA. Perfect. And structures and enumerations are value types. So here's a good example. Let HD resolution, and we can go ahead and make a instance of this, and then we can actually assign that to another variable, which is kind of interesting. So let's go ahead and play around with this. Let's move everything down a little bit. So in this particular example, what we will do is instances. We'll say first, let HD, and we make an instance of the resolution, and we set the width and the height. But to make things more interesting, we make a copy of that instance, and we have a mutable variable. And the reason we would do this is that we want to mutate that value. So that is pretty cool, actually, with Swift, is that you can make the initial instance immutable, but you can make the copy of the instance mutable by just making a var and making a copy of that. And so now if we go ahead and we print this out, we can see that in fact that value has stuck. But if I wanted to, for example, mutate the original instance, hd dot cinema, let's go do that. hd dot width here, and if I said 2048, it'll blow up. There we go. It will say can't do that because this is a let, right? So pretty neat that that you can decide cannot set, right? You can decide whether you want that instance to be mutable or immutable. You can first make it immutable by using let, and then you can make a copy of it and then make it mutable. So I think that's a cool feature that we have of that. And so you can see here there's a flow diagram as before. The initial resolution was 1920 by 1080. But then afterwards, because we made a copy of the HD instance, we're able to set the width to the cinema resolution, which would be 1080 by 1048. You can do the same thing with enumerations. They're pointing out here, right, where you can make an enum, make one of them immutable. I'm assuming that's what they're going to do next year. Make an enum here called compass point, have a case statement, north, south, east, west. We make a var here of the current direction of compass point west. And then we say let remember direction. So what are we doing here? So the idea would be that you can set a copy of the original value. So that's really the main takeaway. So classes are reference types. Unlike value types, reference types are not copied when they're assigned to a variable. They're passed to a function. And so in this case, here's the video mode class. So we can go ahead and make that immutable. So let's go ahead and play around with this. We're going to say let 1080 equal video mode, 1080.resolution is equal to HD, 1080.interlace is equal to true, and then 1080.name is equal to 1080i. So let's see if that works. It does. So this declares a new constant called 1080 and sets it to refer to a new instance of the video mode. This video mode is assigned a copy of the HD resolution by 1080 before, and it's set to be interlaced. So you can also do, in this case, assign a new constant. You can say let also, and go ahead and assign that a new constant as well. What do we have here? We have, because classes are reference types, 1080 and also 1080 actually both refer to the same video mode instance. Effectively, they're just two different names for the single instance as shown in the figure below. 1080 video mode resolution HD interlace true, name equals 1080i, frame rate after 1080 also 1080. So checking the frame rate property of 1080 shows that it correctly reports the new frame rate of 30 from the underlying video mode instance. In this case, we want to say the frame rate property of 1080 is now 1080.framerate. Here we go. We could say this example also shows how reference types can be harder to reason about. If 1080 were and also 1080 were far apart in your code, it'd be difficult to find all the ways the video mode has changed. Whenever you use 1080, you also have to think about the code that also uses also 1080 and vice versa. In contrast, value types are easy to reason about. So yeah, that is one of the issues, is when you get into object-oriented programming, you have to consider about mutation. So identity operators, because classes are reference types, it's possible for multiple constants and variables to refer to the same single instance of a class behind the scenes. This isn't true, though, for structures and enums because they're always copied when they're assigned to a new constant. So they're not mutating things behind the scenes. So it can be useful to find out whether two constants and variables refer to the same instance of a class. To enable this, Swift provides two identity operators. So basically, that is pretty cool. You can see, like, are these two instances the same thing? In this case, we can say they refer to the same video instance by using this triple equality operator. That is pretty nice. So in a nutshell, I learned a lot by playing around with structures and classes. I think the main thing that I would agree with from, I'm just reading what the language authors say here, is that unlike other programming languages, Swift doesn't require you to create a separate interface and implementation for structures and classes. And so in general, they're telling us that the classes themselves can really cause an explosion of complexity because of the ideas of, you have behind the scenes some object that can get mutated accidentally. And so their recommendation is prefer structures because they're easier to reason about. Only use classes when they're appropriate or necessary. So I'm going to definitely follow what they tell me. Is I'm going to use the structures because they're what they recommend. So thank you, Swift documenters. I'm going to follow your lead. All right, so that's